All right, section 3.2 is called maximum and minimum values. Now, the test that I just gave back to you, one of the questions, true-false questions you had on there, talked about the fact that if you have a derivative that's 0, it doesn't necessarily mean you have a max or a min, right? But if you talked about it the other direction, that's actually a very helpful piece of information. If you did have a max or a min, it would in fact have had a slope of 0, or if it had a sharp turn, it would have had a slope that was undefined. So that's actually where we're going to start this piece of information. We're going to be talking in this section about relative, and you see in parentheses the word local. Those are interchangeable words. Extrema. So extrema just means maximum or minimum, okay? This is a gender neutral, if you will. It's a more general term for maximum and minimum. We can call it extrema. So if we have a point C, f of C on the interval, where it is a maximum or minimum value, then that's called a relative or local extreme value. Notice, when we do this, the derivative is either 0 or it doesn't exist. So if we have a place where we do in fact have a maximum, it would look something like this, or it could look something like this. It either has a smooth, curved place where it changes, in which case I get a derivative that's 0, a tangent line that's flat, or I get a place like this where the tangent line won't work, and I have a slope that doesn't exist.
So the maximum exists, obviously, just not this tangent line.
Exactly. So we can still talk about it being a maximum, but we would talk about it being a maximum because it either has a derivative that's 0 or because it has a derivative that doesn't exist. And I could draw these pictures for a minimum just the same. I just flip them upside down, right? Okay. So if we're actually trying to find places where we have maximum or minimum values, then that means we can find these places where it has derivatives of 0 or derivatives that don't exist. So the process by doing that is actually looking for what's called critical numbers. Critical numbers are the places where the derivative is 0 or where the derivative doesn't exist. These are locations where there are potentially relative or local extrema. Now the word is potentially because we could still have that same graph that many of you identified, right, like y equal x cubed, where we do have a derivative of 0. Absolutely, looks like right here, derivative 0, it flattens out, but this is not a maximum or minimum. So this doesn't necessarily ensure we will have a maximum or minimum. It just shows us places where we might have a maximum or minimum. All places. Okay, so if there's a maximum or minimum, it's going to be fleshed out when we do this process.
Is there any graph that does that twice?
Sure. You'd have to have at least a power of 5. So just imagine taking this and doing it, like you said, twice. Yeah, and it would have to at least be a power of 5 to do that. All right, let's take a look at an example so you can see how this works. Direction set says to find all critical values, or critical numbers, by hand. Use your knowledge of the type of graph to determine whether critical number represents a local max, min, or neither. So we'll talk about how that works in a minute. But let's take a look at the first one. So finding critical numbers by hand means, this phrase, means taking a derivative and setting it equal to 0 or equal to doesn't exist, depending on the function you're working with. Now, the function that we're working with here, is a polynomial. So this polynomial doesn't have any sharp turns. Agreed? It's continuous and it's differentiable everywhere. We've established that back in chapter 1. So we don't have any does not exist values on this, and we're just going to have derivatives of 0. So what is the derivative of this function?
3x squared minus 6x.
Good. 3x squared minus 6x. And what we're going to do is we're going to set that equal to 0 and solve. So how do I solve this for 0? Good. I'm very glad, Stephen, that you said factor. We do not want to separate this and divide, and the reason we don't is because we'd have x on both sides. We don't want to put x on both sides of an equation, okay? We need the x's to be collected to one side, and they already are. So we're going to factor out a 3x, which would be what's left in parentheses then?
X minus 2.
X minus 2, perfect. So then what do I do?
Set each of those equal to 0.
Good. So what does x equal? 0, and 2. Okay, so far so good? Excellent. So, what are we going to do? Well, one of the things excuse me, to do is to determine whether this, it said over here, whether it represents a local max or a local min. Agreed? All right. This graph, what do you know about this graph? What in the world happens on the edges, the very ends of this particular graph? It's cubic. Agreed? So what happens on a cubic graph to the ends of a graph? One goes up and the other side goes down, right? One approaches infinity, the other side approaches negative infinity. How do we decide which side does what? Do you remember? On which part? Do you remember, Aaron? Right. So it's all about the cubing because it's the biggest exponent. So if it's positive, it's got either like this or like this going on, right? And if it were negative, it'd be flipped upside down. So ours is a positive x cubed. So our graph goes down on the left and it goes up on the right. Agreed? So if we do have a max or a min, then the places where we have maximums or minimums would have to be, the first one would be the maximum and the second one would be a minimum. Everybody good so far? It's the only way that's possible. Here's something else of interest, and this actually comes right back to Will's question just a moment ago. Can it have two flattening out places? And the answer is yes, it could have two flattening out places, but when did I tell you that would have to happen?
Power of 5.
At least a power of 5. So I can't have two flattening out places if I've got a cubic power here, and I do in fact have two places where my slope's 0, right? So I am in fact going to have a maximum, and I'm going to have a minimum. It's going to have to happen. So as looking at my answer, this value right here is to the left of, and this value right here is to the right of. Right? I mean, it's right of the other one. So this one is on the left, this one's on the right. So this x equals 0 is this first location, which means at x equals 0, I've got a max. And at x equals 2, I have a min. Now, I want to pause for a moment and make an observation with you. This maximum and this minimum at x equals 2 and x equals 0 are not the absolute maximum and absolute minimum of this whole graph. Okay? So let's just take this picture, for example, and take a look. This location right here, where I've got the first maximum point marked, is not the biggest value on this graph. Is it? There are bigger values over here. And the place where I've got the minimum is not the minimum of the whole graph. There are smaller values over here. That's why this is called relative or local. Okay? So I'll give you an example of where this is something that's come up in my life. When we moved to Ohio, my husband was a youth pastor, and my mom came to visit one time. And in my family, I'm tall. Some of you boys have stood up next to me. Am I tall? No, I'm not tall. I'm 5'4". It's fairly average for a woman, maybe on the short side potentially as well. It's not tall. My mother thinks I'm tall. I'm the tallest female in my family. My mom's 5'2", my sister's 5'2", my granny was 5 foot. I mean, everybody's short. Okay, we're little people. Well, we're short people anyway. Okay, so my mom thinks I'm tall. And so it was very humorous when she came up to visit us when we lived in Ohio, because every single child, quote unquote, teenager in our youth group was taller than me. We had an exceptionally tall set of people in our youth group. But every single female was taller than me, even, the 7th graders. So I had to tell my mom, I am not tall, right? In comparison to my family, she said I am. That's called a relative extrema. It's what you're comparing with, right? It's all about what the comparison is. Even you boys who are in this class who I would say are tall, if I sent you over to visit with the Thunder basketball team, all of a sudden you would not quite feel so tall, would you? No, you would feel quite small, very short. It's all in what the comparison is made. So when we talk about a relative extreme value here, we're talking about in a local area. In a small area sort of surrounding it, what's happening? Well, in this small area that I've boxed in surrounding that point, it is the biggest point. So it is a relative or a local maximum value. Does that make sense? Same thing for the minimum. All right, there's one other thing that we need to do. We need to find the final answer to the question. So we've actually identified that there is a maximum value at x equals 0. There is a minimum value at x equal to 2. And what we want to find is we want to find the actual y value that goes with it. Okay, we want to find the location of the actual point. You guys with me on that? How do I find the y value when x is equal to 0? Yeah, I plug it into the original function. So I'm going to evaluate what is f of 0, and I'll do the same thing for 2. What is f of 2? So we're looking back at our original function right up here. If I plug in 0, what do I get?
0.
Yeah, I actually get 0 on that one. That doesn't always happen, right? What if when I plug in x equals to 2? I get negative 4. So what I can say is that I have a relative max at 0, 0, and I have a relative min, and you can use the word local if you want, relative min at 2, negative 4. And that's the answer to the question that's being asked. It's incomplete if you don't give the y value that goes with it as well, okay? Because it's just telling you the location in terms of x, and we want the point on the curve. All right, any questions on that one? Okay. All right, so one of the things that you mentioned, Chance, is that when we take a look at these particular y values, the outcome, obviously 0 is bigger than negative 4. So we would say since 0 is bigger than negative 4, 0 must be the max and negative 4 must be the min. And when we deal with some functions, that actually is an acceptable way to look at that and make that decision. But there are some graphs for which it isn't. So let me draw you a picture where we couldn't make that claim, okay? Let's say our graph was not a polynomial, and let's say instead it was a rational graph that looked something like this. So it's got sort of this asymptote horizontally going on there, and it has a vertical asymptote like that. I'm sorry, not the horizontal. That's not appropriate. That's not what I wanted. I wanted a slant one. This is a terrible picture, but imagine you've got some slant asymptote going on. On this particular graph, this one is the relative minimum, right? Just picture-wise, right? It's the smallest point in its little local area. It's the minimum. Over here, this is the maximum because it's the biggest point in its local area. The problem on this picture is, do you see that my minimum is bigger than my maximum?
True.
Yeah, and that's kind of weird. It's a weird case. I mean, it doesn't happen for polynomials like this, but in a rational function, it is a possibility of something that could happen. So you can't look just necessarily at the corresponding y values and say, oh, look, the smallest y value, the biggest y value, smallest is min, biggest is max. It doesn't work that way in general. You have to use your knowledge of the function itself. Right up here where it talks about your knowledge of the type of graph, that's what makes the decision for you. So that's when we were actually drawing that this graph would have to have a picture that looked like this because, number one, it's cubic. Number two, it has two places where it has slopes of 0. And number three, the cubic is actually a positive cubic graph. So this is the image that we have to get based on our prior knowledge of what cubic graphs do. Because of that, we can actually take a look and say, I've got these two locations, and whatever the one is that's first is going to be my maximum, and whatever the one is that's second is my minimum. And along a number line, x equals 0 comes before x equals to 2. So 0 is the one that comes first, moving from left to right, so it has to be the max. And 2 is the one that comes second, moving from left to right, so it has to be the min. That's how we're making that call.
Even if the 2 value was up higher?
Correct. Now, that can't happen on a polynomial graph. But it could happen on, like I gave you this example of a rational function graph.
Okay, so
Yep.
it's more like looking left to right, max comes first.
It wouldn't necessarily be max comes first. It depends on the graph. Like if I had the graph that did this, same graph, but I had a negative in front of the x cubed, then the minimum would come first. And so moving from left to right, I would identify that, look, here's the x value, and let's say that this is x equals 3, and this is x equals 7. Well, I'm going to have my minimum then at 3, and I'm going to have my maximum at 7. So it's really a prior knowledge of what the picture sort of has the general shape of to make that call. Yes, Luke?
Is this the right way of thinking about it? The way I did it, I set up like a little table, and then I do like negative infinity to 0, 0 to 2, and 2 to...
Yep.
You know what I'm talking
And
about?
we're going to have one like that later, but
Okay.
I don't think it happens in this section.
And
I
then
think
we
we're going to
just have
talk.
draw
We're
the
going to talk about
arrows.
that idea in 3.3. Yes, yes, that's exactly what we're going to look at
Does
in
it work for
3.3.
everything too, all cases?
Trying to think if there's any exceptions. I'm not thinking of any exceptions right now, so I'm thinking the answer is probably yes to your question. Yeah. All right, let's find another one, and this one is going to be a rational function, so it may have that sort of weirdness going on that I described. I'm not sure. I don't remember if this one does or not, but it is a rational function. All right, so same directions. We're supposed to find the critical numbers, and the difference is that it says if available, we're going to use a graphing technology to decide if it's a local max or min. So we're going to use our calculators for this one now, okay, to give us some helpful sort of hints. All right, so this one actually is f of x equals x squared minus 2 over x plus 2. So on this one, we're still going to do the same thing. We're supposed to find the critical numbers by hand. So what does that mean? It means take a derivative and then set it equal to 0 and solve. That phrase is what that means. Take a derivative, set it equal to 0 and solve. So what is the derivative? What rule are we going to use to take this derivative? Quotient rule. All right, so somebody tell me how I'm going to use the quotient rule. Compared to the ones you did on your test, this is simple, right? What is this?
X plus 2 times 2x minus squared plus 2 times 1.
Perfect. And that's your numerator, right, Will?
Over the denominator squared.
Mm-hmm. Does that look good to everyone? Okay, great. So we're going to clean this up now, simplify. So let's clean up and simplify that numerator. So that numerator, I get 2x squared plus 4x minus x squared plus 2 over x plus 2 squared. It is not at all helpful to FOIL that denominator out. I had told you on your test, some of you actually decided to simplify the denominator, quote unquote, by multiplying it out. It actually creates a bigger mess, and especially for what we want right now, factored form is much more helpful. So we're going to leave that denominator without simplifying it. But my numerator simplifies. What do I get in my numerator?
X squared is 4x plus 2.
And my denominator is still the x plus 2 squared. So I'm going to have critical numbers when this derivative does what? Equals 0, or when it doesn't exist. Now, the reality is on this one, when it doesn't exist, I'm actually going to get asymptotes because the denominator, gives me asymptotes. But we're going to work through the problem and show you how you would test either way to make that decision. Okay? So we need to set this function's derivative equal to 0, or find out where it doesn't exist. So when I have a function like this, and I want to know where it's equal to 0, where in the world do I find places where a function like this is equal to 0?
So the numerator equals 0.
Right. It has to happen if the numerator is 0. Now, I'd love it if this factored, but it doesn't. So now you're going to pull out some algebra that you know from ages back. What do you do when it doesn't factor?
Use the program.
You could use completing the square. That's a very ambitious answer. I don't think anybody usually does that. But you could. It's not a bad one to complete the square on. The other thing you could do is to use the quadratic formula. So, Luke, why don't you complete the square?
It's okay.
Okay, you don't want to do that? All right. Let's use the quadratic formula. Guys, remember the quadratic formula?
Nope.
Nope. All right, I'm going to write it down for you, and you can jot it down. This is x equals negative b plus or minus the square root of b squared minus 4ac over 2a. So that's the quadratic formula. Maybe you remember some sort of song that goes with it. Yes, the song is great. I think I'll decline from singing it today. But there is a song that goes with it. So we're going to use that on our equation up here. So x equals, what is b in our equation? 4. 4. So this is negative 4 plus or minus the square root of b squared, so that would be 16, minus 4 times a is 1 and c is 2, all over 2 times a, which is 1. Let's simplify underneath the radical. What do you get when you simplify underneath the radical?
No, sorry,
8. All right, and outside, and then you've got the 2 underneath there. How do I simplify the square root of 8?
Choose correction.
Yes. So remember that this is going to be equal to 4 times 2, and then the square root of 4 is 2, so the 2 can come out. There's other ways to remember it, but that is one that works. And then this is over 2. And then you notice that every piece of this has a 2 in it, so you can reduce them. So this ends up giving you negative 2 plus or minus the square root of 2. Isn't that a fantastic value? Or something like that, right? Okay, you guys ready to take a look at the other one?
But it's actually, is it 2 values?
It is 2 values, yes.
Okay.
So you have negative 2 plus the square root of 2, and you have negative 2, minus the square root of 2. You're exactly right. That is 2 separate values that we've got in there. Let's take a look over here then at the other one. How in the world do I find where a function doesn't exist, or where this function doesn't exist?
Denominator.
The denominator equal to 0. So where in the world will this denominator equal 0? At negative 2. Now, the kicker is that we recognize right now that this is an asymptote. And so if I have an asymptote, I don't have a slope of anything, right? There's not really even a point there. It doesn't work with the function. So this doesn't give me any new information. This is sort of unhelpful for the discussion right now. Okay. Now, there are cases where I would have a denominator equal to 0. In particular, if you'd had something like you took a derivative of square root, and then when you take the derivative, the square root becomes something in a denominator, like the denominator wasn't there originally, where you would actually get a value that would be useful information. On this one, you just simply don't. All right, so the question was going to be then about whether or not we get a maximum or minimum value. So I want you to grab your calculator, and I want you to put the original graph into the calculator, okay? Original graph of x squared minus 2 over x plus 2. And somebody describe sort of visually what you see when you do that to me. Put it in a standard window. I think a standard window is appropriate. I don't remember for sure. Is it? Excellent. What kind of overall picture do you get?
Similar to what you did earlier.
Kind of similar to my picture before.
Yeah.
Yeah, and if you take a look back at the equation, that should make sense. The equation definitely has a asymptote at x equal negative 2, right? And it has a slant asymptote because the numerator's exponent is higher than the denominator's by exactly 1. So when we did slant asymptotes back in chapter 1, and we talked about that. So that makes sense as well. So taking a look then at your graph, the first point, that is the point on the left, did it actually look like, in fact, let me just graph it too. All right, so it's sort of the flip of what I drew, right? Here's the asymptote going like this. I've got sort of an asymptote going through here like this, and I've got a trapped graph that looks something like this. Does that look about right? I know I don't have my axes on there, but I don't really need my axes on there. The axes look something like this. However, I'll draw it in purple. All right, so this point is a local max and this point is a local min. Everybody agree visually that that's what we've got going on? The question is, which of these two ordered, or not ordered pairs, but which of these two sort of funny looking points with square roots corresponds to which of these 2 points? So this one right here, which of these x values is that one?
Negative 2 minus square root.
Yeah, this one, because this is smaller because of the subtraction of the square root of 2 instead of the addition. So this location is the negative 2. X equals negative 2 minus the square root of 2. This one over here is x equals 2, negative 2, plus the square root of 2. So when we're taking a look at our answer, this one, I'm not going to go ahead and find the y value. The reason is because it actually just said critical numbers. I recognize this one said critical numbers too, and I kind of went one step further and said let's find the y value because it was simple to do so, not because I was asked to do so. On this one, it's kind of messy to do so, so unless they actually tell me to, I'm not inclined to find it. How do you think about that? Sound good? Okay, if they wanted you to find it, they would have to actually say critical points because a point is an ordered pair x, y. And they said critical number, which is just the x value, so x is sufficient for this problem. And since it's not convenient or simple to find it, I'm not going to. So my relative max is at x equals negative 2 minus the square root of 2. What's that? Did I write something differently? What do you?
So when we look at the whole graph, obviously that's not the max of the function.
Correct.
It's the relative max.
Yeah. Moving things around in a way that's not working. Yes, it is a relative max only. And then I have a relative min just in the local area itself at the negative 2 plus the square root of 2. And since they didn't ask me to find the y values, I'm not going to since it's kind of a messy one to do with the square roots involved. Any questions on this one? Because we're about to encounter a sort of a difference of what's going on next. Okay. As we've hit on multiple times, relative extrema only matters if you're talking about a local relative area, small space around it, so to speak. If you compare something on the ends of these graphs, it may not actually be the biggest or the smallest value on the whole graph. So what in the world could we use to describe something that really is the biggest or the smallest? We use the word absolute, the absolute extrema. So a point is the absolute maximum if it's the biggest point on the entire graph or on the graph's interval that you're looking at. A graph has an absolute minimum if you're looking at the very smallest point on the graph. And the extreme value theorem, so we've had the intermediate value theorem, we've had the mean value theorem, and now we have the extreme value theorem. The extreme value theorem simply says that if your graph is closed, that is, if it doesn't go up and down forever, right, it's actually stuck between two different x values, that it will in fact have a place where it has the biggest value and it will have a place where it has the smallest. It has to. That's all the extreme value theorem says. There is a place where it is the biggest, there is a place where it is the smallest, but it has to be a bounded interval. So it has to be a trapped amount of space for that to be a for sure thing.
So does that ever naturally occur in functions? Or would you have to bound it by giving it an interval?
There are functions like sine, if you take a look at sine, that has an absolute maximum and an absolute minimum, where it actually forces the top and bottom to be bouncing up and down. You can actually look at that too on some natural functions like the graph of an exponential, where it asymptotes out on the left or the right, it flattens out, or one of those graphs where it actually has an absolute maximum or minimum in that way. Rational functions don't really do that because they usually go in both ends. They extreme in both ends, but flatten out in both ends one way or another. But exponentials will, yeah.
Like the graph of x squared have an absolute minimum.
It would, but it wouldn't have an absolute max.
Right.
So the extreme value theorem says that it's going to have both. So that's actually a pretty strong statement. And it only works in general when you're dealing with something that's closed, a closed interval. It's kind of like making the statement that you're the tallest person. Well, the tallest person compared to whom? The tallest person at OBU, the tallest person in Oklahoma, the tallest person in the world. You'd have to kind of close off the comparison that you're making in order to make the statement at all. It's kind of like that. All right, we're going to take a look at what this means. In order to find a actual extrema, so if you're asked to find the extrema, we actually have to test for the relative extrema first, where places where we have these maximum or minimums in the local areas. And then we have to test the endpoints second. So there's two things we have to test. We have to test exactly like we were doing on problems 1 and 2. But then we have this additional step at the end where we also have to test the endpoints of our interval. And we're going to work with a cosine graph, which naturally has a bound, kind of like we were just talking about. But we are working on it on a closed interval. Are you guys ready for me to look at the next slide? Well, you're still writing. I'm not wanting to rush you. I'm sorry. Are we good? Okay. I've got a cosine graph. This cosine graph, tell me what you visually know about this cosine graph. Let's just start there. What's it do? It goes up and down. Between what values?
3.
Why, Noah? Why is it 3? Right, the 3 at the front changes the amplitude, so this is going to be going up and down between 3 and -3. So I know that my absolute maximum, if I looked at the whole graph, would be 3, and the absolute minimum, if I looked at the whole graph, would be -3. Agreed? But we're actually wanting to know on this particular interval what the maximum and minimum are, and it may or may not be 3 or -3. Okay? So we're going to take a look at this from that perspective. So we're going to take our function, and we're going to first find, step number 1 is to find the relative extrema. This is a two-step process. Every time we're finding our absolute extrema, we first find the relative. How do I find relative extrema? Find the derivative. All right, so what is the derivative of 3 cosine x? Good, -3 sine of x. So I found my derivative. Now what do I do with my derivative? I set it equal to 0, and I solve. Now you have to think about your unit circle, okay? Or about the sine graph itself if you know something about sine graphs. Where in the world, and the -3 is unimportant here, agreed? Because I could divide the -3 on both sides. So this is really asking the question, where is sine of x equal to 0? Does everybody recognize that? So somewhere in trig you solved equations like this. It was probably somewhere in the close proximity to where you did like identity, verifying or proving identities. You probably liked this a little better than that part. Where does sine have values of 0?
0 and pi.
Uh-huh. And 2 pi, and 3 pi, and -pi, and -2 pi, and -3 pi. So on your unit circle, it's every time you hit the x-axis, right? So it's on the left-hand side and the right-hand side of your x-axis on the unit circle, and it happens repeatedly. It just keeps going round and round. We keep hitting the x-axis, right? All right, so taking a look then at this, the values that are perhaps the most important ones for us right now are going to be the values that happen to be between the values we are looking at on our interval. And that's not all of these values. So we only care about the values that are between pi over 2 and 5 pi over 4. Which of these values are between there? Pi. And no others, right? Pi is the only value here between, and I don't have a notation here, right? This is at x equals, not sine x. Please make that fix on your notes too if you were copying mine. The angle at 0, pi, 2 pi, 3 pi. So this is the only value that's actually between pi over 2 and 5 pi over 4 is pi. Agreed? Now's the time to ask if you don't agree or you're not sure what I'm talking about. Okay? So this is one of my values. And what I want to know is I want to know what in the world is the y value at that value of pi. So it should be 0. I mean, agreed, that's kind of the point. It shouldn't be 0. The slope is 0, but we want to know what the y value is on the graph itself. So we're going to take g. This is sort of step 2. Let me write it this way. Well, this is the end of step 1. Let me pause for a second. This is the end of step 1. We want to know what is g of pi. So my g function was 3 cosine of x, so I want to know what is 3 cosine of pi. It's not 0. I mean, it could be, but it's not in this one. This one's 3. I think it's negative 3. Negative? Yeah, because its cosine at pi is negative. So this is negative 3. Okay, so this is one y value. Step 2 is to test the endpoints. So my endpoints are at pi over 2 and at 5 pi over 4. So I need to find out what is 3 cosine of pi over 2 and what is 3 cosine of 5 pi over 4. So we'll start with 3 cosine pi over 2. What is 3 cosine of pi over 2? It is 0. What is 3 cosine of 5 pi over 4?
0.
No, it's not 0. That would be nice. It's 3 times something. Do you remember what the cosine of 5 pi over 4 is?
1/2.
No.
Negative square root of 2.
It is negative square root 2 over 2. Unit circle, if you haven't looked at that in a while, would be a good time for you to do that, I think. So this ends up being negative 3 square roots of 2 over 2. That's what that is. So here's the deal. Once we've tested the endpoints and we've found the corresponding y value for the relative extrema, we take a look at the 3 y values that we have. And this goes back to what you were asking about, Chance, when we were doing relative extrema. What we did and we talked about with relative extrema is it didn't work. It didn't always give me what I was hoping it would give me, but for absolute extrema, it does. Looking at these 3 values, which one's the biggest?
0.
0. The biggest is my max. Which one is the smallest?
Negative 3.
Mm-hmm. Nope. This one is my smallest. It's actually at negative 3. The smallest is my min. So we just compare the y values. Whichever one's the biggest is the absolute maximum. Whichever one's the smallest is the absolute minimum. So my answer is that my absolute max is pi halves 0. And my absolute min is pi negative 3. So there's two ways of testing the points. You have to test the endpoints, and you have to test all of the relative extreme values. If you only test one or the other, you're likely going to lose part of the answer in the process. Yes, Chance?
So whenever you chose pi,
Uh-huh.
is that because those values are like in between, like from 0 to pi?
It's because these values right here, if I were looking along on a number line and I put in pi over 2 and I put in 5 pi over 4, I only want to be between these values, and the only one of this list of values that's between them is pi.
Oh,
So I have to only pick values between them because I'm on a closed interval, only considering the values between them. It's kind of like saying if I'm the tallest person at OBU, and then somebody says, yeah, but I know this guy at OU, and you're like, yeah, I wasn't talking about OU. I was talking about OBU. So you're sort of going outside of the area if you were to look at any of the other values, and we only care about the values between. Okay? All right, one more example. These are the ones that make you guys a little bit uncomfortable because multiple answers are possible, and you never are sure if you really have the right answer. Because it doesn't match your neighbors or something like that. So let's take a look at what we've got. This one's got a little bit more concrete pieces to it. It says we're going to sketch a graph of a function with the following characteristics. The function has an absolute maximum of 3. This is telling you the y value. It is a maximum y value of 3. It occurs on the interval negative 2 to 2, so it's happening between the x values of 2 and negative 2. And the absolute minimum does not exist. And when it says it right here, it means on the whole graph. Obviously, it has to exist between -2 and 2 because the extreme value theorem says so. But this is talking about an entire graph. It does not have an absolute minimum. What that means is that the graph has to actually continue going down forever at some point on your picture. Maybe not on both ends of it or something, but at least at some point on there it has to continue going down forever. So, what kind of graph are you picturing as you draw this?
Upside down parabola.
I think that's a good picture to have. Let me get my graphs back on here. I was using this for something else. All right, so you're picturing something like an upside down parabola, perhaps, right? An upside down parabola would have an absolute maximum without worrying about the -2 to 2 part, right? And it would have an absolute, not have an absolute minimum, for sure. So one possible graph that you could do, and it has to be happening between 2 and -2. Is it somewhere between 2 and -2? I have a peak on my graph. This is one way to draw it. So maybe it happens here. Maybe it doesn't. I don't know. But it has to happen somewhere. And on the graph, otherwise, it might look like that. Is this the only graph? Well, absolutely not. I could actually have a graph that does this. It's not a very good arrow at the end there, was it? This has to be at a height of 3. That is a necessity because of the way it's described. Does that have an absolute maximum between -2 and 2? Yup. Does it extend down forever? Yup. Yes.
So you said an absolute maximum does not exist, but couldn't it if it like had asymptotes on the insides of it, maybe 2 and 2 would just go down forever?
You mean if it had, like if you had something trapped right like this,
Yeah.
That'd be another graph. You could do that.
Okay.
It would still have an absolute maximum. Now, the way that they've described this is a little unclear. They tell you it has an absolute maximum, but they didn't tell you the absolute maximum is the absolute maximum only on the interval or on the whole graph. So if they specified that the absolute maximum on the whole graph is 3, then this picture would work. This picture probably wouldn't because we're sort of intending that the graph continues going up right here, and on the interval it's -3. If we really drew it the way I drew first, it would be fine though, right? If the graph really has no other value to the left of -2, it would still work.
And so are the minimum of the entire graph on the one on the left, is it -infinity?
Mm-hmm.
Oh, okay.
Yeah, and since that's not an actual value, that's why they say the minimum doesn't exist. Because -infinity isn't a particular number, right? It's just a concept of going down forever, of getting infinitely smaller. So this does not have, neither of these graphs have an absolute minimum. Now, if you wanted an absolute minimum on the interval, then you, like saying that the interval itself didn't have an absolute minimum, you would need those asymptotes that you just mentioned. Like that would be a requirement, right? It would start to look something like a part of a cosecant graph or something like that, so that you'd have it trapped between those asymptotes. So you could still get the graph, it would just be something slightly different. Any other questions in that one?